Good evening, boys and girls. This is Mr. Meyer from the Plush Studios of Way Happy, and we are doing Section 8.5 Polar Equations of Conics. That's right, polar equations are back. The R equals, so make sure your calculator is set to polar mode when we want to try to graph these. So let's talk about this. Every conic can be defined as a set of all points whose distances are from a focus to the directrix. And they would have what is called a constant ratio. And that constant ratio is eccentricity. And so eccentricity, when you find the eccentricity, if it's bigger than 1, you got a hyperbola. If it's smaller than 1, you have an ellipse. And if it's equal to 1, you have a parabola. So let's just make sure we understand this. Any point on the conic section, we'll call it point P. Any point can be related by F to P and P to D. And there's the equation there. That's your eccentricity equation for any conic section. Well, kind of the fun thing is this. If we go into polar form of conics, then you notice that if what we do is we place the focus of the conic at the origin, and then the directrix we find, we'll just call that K. So if we take the focus and we put it at the origin, and then we go ahead and we put the directrix will be K. It might be X equals K, it might be Y equals K, it might be Y equals negative K, it might be X equals negative K. We'll take all that into account in a minute, but let's just do this standard form right here. We can now relay those differences. We can measure the angle to P, and we know how far away it is, so we can now kind of switch it to polar form. So the cool thing is that distance PF right there, that becomes just R. And that distance PD that we had, well, that just becomes the distance all the way out to K, but then minus this little distance, which is R cosine theta. And so with that relationship, we can rewrite, remember what we set up here, that eccentricity was PF over PD. So eccentricity is PF over PD. I can go ahead and change just PF to an R, and I can change PD to this. Now I can solve for R. Now it takes a little bit of work, and you end up getting it, and you end up getting this beautiful equation that is the polar form of a conic. That is polar form of a conic. That's it. Magic, right? So if you know the polar form of the conic, all you need is eccentricity and the K value, which is the directrix. You can then have all the equations of the conic. So here you go. That's what this box is clipped out from the book. Now you can see there's that first one we kind of created there, but there's all three of them depending on what your directrix really is. Notice here where it has the directrix mentioned each time. That's telling me which equation I will be using in which situation. So now let's go ahead and try a couple of these and see what we're talking about. And then we'll get the calculator and we'll graph it. So how about this? Write the polar form of an equation whose eccentricity is 3/5 less than 1. So less than 1, that go ahead and that's going to tell me it's an ellipse. Where do I have that written? Right here. Less than 1 is an ellipse. So we know it's an ellipse. And the x value is 2. So what do I know? I know this is an ellipse. And I know that x is equal to 2, so that means we're going to be using this equation. So I'll call it case A. So using case A, we know the equation is R equals K times E over 1 plus E cosine of theta. Now the good news is you know what K is. K is 2. You know what eccentricity is, 3/5. And we put that over 1 plus the 3/5 cosine of the angle. And that's kind of our polar form. Now we got to clean that up an awful lot. So we'll make the top 6/5 over 1 plus 3/5 cosine of the angle. Now that doesn't look too pretty still, so what I'm going to do is get rid of all these fractions. I'll multiply everybody by 5. Multiplying the top by 5, I get 6 over 5 plus 3 cosine theta, and there is my polar equation of this ellipse. And just to show you that it makes sense, I have typed it into my calculator. Again, make sure your mode is in polar form. Hit y equals, and then type in the equation 6 over 5 plus 3 cosine theta. And then if I graph that, maybe I'll zoom 6 it so you see it, and I just zoomed in earlier, and you will see the graph of the ellipse. Done. All right, let's try one more. I can now try this next one where you see y equals 4. So that tells me that I'm going to be using this equation, or Kc, and it's also telling me I'm working with a hyperbola. So we know that this guy is a hyperbola, and it's Kc. So r equals Ke over 1 plus e sine theta. And so now I'm just going to fill in all the parts I know. I know K is a 4, so 4 times 3 over 2 all over 1 plus 3 over 2 sine theta. Again, clean that up. So 12 halves is 6 over 1 plus 3 over 2 sine theta. I don't like that denominator to be sitting there with 2 in it. So I'm going to go ahead and multiply everybody by 2. 12 over 2 plus 3 sine theta. And now I can graph this hyperbola in my calculator. Now this one I haven't typed in yet. So y equals, clear this guy out. I go alpha 1 to get the fraction button. 12 over 2 plus 3 sine of theta. Hit graph and enjoy this amazing hyperbola, which looks like I can't see much up there. So I'm going to have to fix it a little bit. So I'm going to have to change my window. Looks like my y value should have been a little higher. So let's change it to 20. Oops, or 2. That works really well. Change my window to 20. And I have the beautiful graph of this hyperbola. All right, let's give you one. And I'll see you in a few. Excellent work on that last problem. All right, now how about this? Let's determine the eccentricity and the type of conic that we have, and then we'll also get the directrix. Pretty straightforward, just like before, you're just plugging numbers in. But notice what's going on here is when I have these equations, it's usually, let me scroll up real quick, but look at this denominator, 4 minus 3. Up here, it is usually on these equations 1 plus or 1 minus or 1 plus or 1 minus. So we need to fix that. Well, easiest way, divide everybody by 4. So if I divide everybody by 4, I get 6 over 4, 4 over 4, minus 3 over 4 sine theta, which of course we will reduce that and get 3 over 2, 1 minus 3/4 sine theta. And if you know your formula, you know that this is of the form r equals K times eccentricity over 1 minus eccentricity sine theta. So right away I'm given the eccentricity. The eccentricity is 3/4. Woohoo! Right? And excuse me, with the eccentricity being 3/4, I know that this is an ellipse. But even more fun, now that we know eccentricity is 3/4, we could also use the numerator to find out what K is. So I know that K times eccentricity is equal to 3 over 2. And I know the eccentricity is 3 over 4. Then why not just multiply everybody by 4 and divide by 3 and get K is 2. And now I know the directrix. So I can go back up. This is a 1 minus e sine theta. So 1 minus e, there it's sitting right there. So I know the directrix is y equals negative something. So now I will scroll back down and tell you what it is. It is y equals negative 2. So not only did I get the eccentricity, I got the shape, and I got the directrix. And we are set perfect with that example. All right, last but not least, a little trick here too. Let's find the polar equation of this next guy. And what I'm going to do is remember something about this, and probably two things, is that we are going to sit with the focus at the origin, and then we have a vertex at 4, 0. Now be careful, that's your r and your theta. So in the 0 degrees, you want to go out 4 units. And in the pi degrees, you want to go out 2 units. So that's what your ellipse looks like. It looks like something like this. So I know the ellipse. Now the good news that I can kind of tell from this graph, we can see that from vertex to vertex, that's 6 units. So that's probably going to be helpful in helping us figure out some parts of the equation. We could figure out the center, which 1, 2, 3, 4, 5, 6. So go back 3, 1, 2, 3. There's your center. Your center would be sitting at the point 1, 0. And then we look at this graph and we try to figure out what case it is. So if I scroll back up again, notice what we got here. We got the vertex to the left there. And so if I go ahead and scroll up to our different graphs, we don't have this case. Oops, we don't have this case. We don't have this case. Oh, look at that. We don't have this case. We're talking about this case right here. So this is the formula I need, case B. So now that I know it's case B, I can go back down and start hopefully filling in all the stuff that I need to know in order to make this equation. So case B is R equals KE over 1 minus E cosine of theta. Alright, I think I can figure out E, right? Because E is just C over A. So the distance to the vertex and the distance to the focus. Well, we know the center. We know the distance to the vertex is 1, 2, 3. We know the distance to the focus is just 1. So there's our C, there's our A, and I now know the eccentricity is 1/3. So now that I know that's 1/3, I can kind of fill in some stuff. K times 1/3 over 1 minus 1/3 cosine of theta, and we're looking pretty good, except for the fact that we don't know what K is. Well, that's why it's so nice to be given some points. You can always plug in an X and a Y, or in our case, an R and a theta. So I will plug in the R theta. So R is 4, and when theta is 0, so I will have K times 1/3 over 1 minus 1/3 cosine of 0. And we know the cosine of 0 is 1, so therefore we have 4 equals K over 3 over 2/3. At that point you can just really ditch the thirds or multiply by 2/3 on both sides, which is probably more common. So 8/3 equals K over 3, and all of a sudden I notice that K is 8. And I can go back to our original equation, and I can finally put an 8 in there and a 1/3 in there. So here we go. What can I use now? Green. R equals 8 times 1/3. I guess we could just change that to 8/3. 8/3 over 1 minus 1/3 cosine of theta. Now the only bad news is I don't like all these thirds, so let's multiply everybody by 3 and get 8 over 3 minus 1 cosine of theta, and that's our equation that we were looking for on this ellipse. Excellent. Now let's try one more and then we'll go to analyzing. All right, nice work on that last problem again. So let's talk about the last part we have, analyzing a conic. So now someone's going to give us a conic in polar form, and they're going to ask us to find out everything like A, B, and C. So we could write maybe the conic in regular form for people who don't know polar coordinates. So in other words, just the old Cartesian. So let's find out all the different parts for them, and it'll give you the little hints, but the way you find the missing parts is you can usually rewrite the conic from its polar form. You can just make sure it fits the 1 plus 1 minus rule on the denominator, and that will get you at least the eccentricity. Then you can usually find the vertices by, if it's a cosine problem, make sure you use the angle 0 and pi, because then you'll be using 1 and -1. And if it's a sine problem, make sure you use pi over 2 or 3 pi over 2 for the same reason, 0 and 1. Once you figure out A, you can now find, whatever you're missing. And so let's show you what I mean by that. So first step, I guess, we could go ahead and I like to find the vertices. I see this is a cosine problem. So the first thing I might do is find the vertices, and I would say, all right, if I'm going to do that, it's a cosine problem, I'm going to plug in 0. So I'm going to get 16 over 5 minus 3, because cosine of 0 is 1, which is 16 over 2, which is 8. That means there's a vertex at the point 8 comma 0 degrees, because remember, I plugged in 0 degrees. Then I'm going to plug in pi, so that would give me -1. So the other vertex would be 16 over 5 minus 3 times a -1, or what most of us would call 16 over 8, which is 2. So that means there's a vertex at 2 comma pi. So there's our two vertices. Now I can also get you the center from that. I can get you the eccentricity by fixing this equation up a little bit. So let's talk about how I'd find eccentricity. I would divide everybody by 3. So you'd have 16 thirds over 5 thirds minus 1 cosine theta. Why that would divide? Now I could find you the eccentricity by modifying this. Remember, I just want to divide everybody by 5. So 16 over 5. 1 minus 3/5 cosine of theta. So now I know the eccentricity is 3/5, which means, hey, by the way, this thing here is less than 1. And if you remember way back in the beginning, less than 1 means you're an ellipse. So we know it's an ellipse. And so now let's talk about, I don't know, what things do we still need? I might throw a little graph out and say, I know that the center, let's see, there's a vertex in the pi direction, you go 2 units. In the 0 degree direction, you go 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's a distance of 10, meaning right in between those two at 5. 1, 2, 3, 4, 5 is the center. It's 5 units in, so 3. So there's my center at 3, 0. Ellipse looks kind of something like this. And now I can find all the parts. So let's see, I got A is the distance to the vertex, which we know is 5. B, I still don't know. C, I can now calculate C because I know the eccentricity. So remember, eccentricity was 3/5, and eccentricity is C over A. And so since I know what A is 5, I got 3/5 is equal to C over 5. A little cross multiplication will get us that C is 3. So now we know that. And then last but not least, since this is an ellipse, I know A squared minus B squared equals C squared. And since I know A and C, I have 25 minus B squared equals 9. So now all I have to do is do 25 minus 9 means B squared is 16. And now that I know that, B must be a 4. And so there is your eccentricity and your ABC. And if you wanted to help somebody out and write this in rectangular form, you would say, hey, it's x minus 3 squared over 25 plus y squared over 16 equals 1. And you have the equation written. Beautiful. Have a great day, and we'll see you tomorrow. Stay happy.